Probably help if I was in the right chat thread. Cool, awesome. Right on. Well, welcome to Monday. This is the penultimate lecture of the course. Wednesday is our last lesson lecture. After that, we've just got a review for an exam, and then some capstone project presentations. So we are definitely pretty much done with this semester, man. It's almost over. Okay. Are there any questions, comments, or concerns before we get things going today? I am indeed recording. Cool. All right, just one thing. Don't forget that we are doing, I still need to send an email to remind everybody of this, but we are going to have our final exam on 1 week from today. So it's not comprehensive. It's just over the stuff that we've done since the first midterm exam. So it's just the back half of the course. We'll do a full review for it on Friday, but that exam is going to be on Monday, 1 week from today, like I said. So right before you take the exam and then go off on your Thanksgiving break. So any questions about that? Cool beans. All right, in that case, let's go ahead and talk today about differentiation and integration. Now, what do we mean by all of that? So let's see, just a quick overview. We're going to talk about this thing called finite differences. We'll look at what that looks like in the frequency domain. We'll compare differentiation and integration, and we'll talk about cumulative sum, which is basically another way of implementing integration in a little bit more of an efficient way. So first, let's look at what we call finite differences. So in the previous lecture, we looked at how applying a smoothing window corresponds to a low-pass filter in the frequency domain, right? So if we average everything, we end up getting a low-pass filter. What we want to do now is kind of look at how computing the difference between successive elements in the time domain, taking the derivative of the time domain signal, corresponds to a high pass. So this should be a high pass filter, not a high pause filter. But you get the idea. So that's what we're going to look at. We're going to look at how do we calculate the difference and how does that give us a high pass filter. So first thing, our first demonstration, let's bust out of our PowerPoint, get into Visual Studio Code. And take a look at some stuff. All right. One thing we need to know is I'm going to need a CSV file that I forgot to copy over. So give me just a second. All right, so let's create a new Python file. Let's call it demo1.py. And we're going to need some dependencies. The first thing we're going to need is NumPy, as always. As NP, we're going to need import pandas. As PD, whoa, what the heck is that? As PD, we're going to import thinkDSP to do our stuff as DSP, and then we want to plot some things, so we're going to import matplotlib.pyplot as PLT. All right. So the first thing we want to do is we're going to import this fb.csv, which has some stock data for Facebook, and we're going to use that as our sort of demo signal for today. But we need to set up importing this into Python. The first thing we need to do is kind of define the column headers, so date, open, high, low, close, adjusted close, volume. So we're going to need to define those columns. So I'm going to say names is equal to date, open, high, low, close, and volume. That's what I want to name each of these columns. So I'm going to say df for data frame is equal to pd.readCSV fb.csv. We're going to say header equals 0, and give ourselves these names. Names equals names. Run that, make sure we didn't screw anything up. Cool. All right. So now we just grab our y's from the closing signal. So I'm going to say y's equals df.close.values. One, because I just want to grab that closing price. Let's say close equals dsp dot wave y's frame rate equals 1. And let's go ahead and plot that. So we'll say close dot plot and plt dot show. Oh, and I need to say y is equal to those closing values. So if we plot it, we get a thing that kind of looks like this, right? So this is our Facebook stock price. We're just indexing, so there's no dates or anything like there. But we can see that it basically gets a signal that sort of, does the stuff. So here's a question for you. What sort of noise does this look like? Yeah, good job, Edward. It looks like Brownian noise. So stock prices have a lot in common with Brownian or red noise. Let's take a look at the spectrum of that. Let's go wait and see what Akil was going to say. I guess nothing. All right, let's take a look at the spectrum and see what that looks like. Oh. Should have typed red noise, Akil. That would have been faster. All right, let's look at the spectrum. Spectrum equals close.make spectrum spectrum.plot. I'm going to shrink in. Well, so what do we think this spectrum is going to look like? Edward's typing. Typing. Are you serious? That was like 30 seconds of watching you type for All right. So yeah. So if it looks like Brownian noise, all right, we're just messing around. Okay. Let's go ahead and plot it and take a look and see what it looks like. Remember, red noise was frequency spectrum in the lower frequencies, and that's totally what we get here, right? We get this sort of frequency that's bunched up all on the low frequency side, and we can even kind of zoom in a little bit and say, let's say plt.xlim to shrink in our x-axis from 0 to 0.05 to take a look at what we got. And there we go. Again, just a lot of low frequency, basically no high frequency component whatsoever. Almost entirely low frequency stuff. So what I want to do now is compute the difference in that. So what I'm going to do now is say diff is equal to np dot diff. So numpy, this is going to take the derivative effectively of our y's, and we're going to make that into a thing. Change equals dsp dot wave of diff frame rate equals 1. Let's go and plot that and see what that looks like. That wasn't part of my plan, but let's do this. Change dot plot. In fact, let's keep our close plot. Change dot plot. And plt.show, and I haven't done this before, so this will be new to me too. Well, that's kind of weird. So why does this spectrum look like this? It's not really a spectrum. Why does the signal look like this? So sort of centered around 0. Ever says the moments that have a high difference means our signal changed a lot. Yeah, so we're looking at the relative difference between data points here, which is why, so when it changes a lot, notice that we have like this big dive down, this like from this peak down to this trough, sort of corresponds to this big negative value here in the signal. Let's take a look at the spectrum of this and see what that gets us. Let me see, spectrum. I want to get rid of that. I want to get rid of that. I want to say change spectrum equals change.make spectrum. And let's plot that. See what that gets us. Interesting. So what does this look like? And this is sort of the punchline of this example, right? Our spectrum of our original signal was definitively just red noise, right? But our spectrum of the differences here is exactly right. It's white noise. Yeah, uncorrelated specifically noise, right? Now you could probably look and see there might be a little bit of the sort of original signal there, but the take home there is when you take the derivative of a signal, or just calculate the difference, not even really the derivative, you're sort of just calculating the difference in those signals, where you're going to get a white noise spectrum instead of the original Brownian red noise spectrum. All right, so let's move on from that, because we want to convert that to the frequency domain here in a second. So from current slide. So let's take a look at what that looks like in the frequency domain. So we can achieve the same effect in the frequency domain through the application of a different window, or specifically what we're going to call a difference window. So we're going to, instead of just calculating the difference and getting that white noise spectrum, we're going to apply a window to it that gets us the same effect. So let's take a look at that. All right, we're going to call this demo2.py, and we're going to import, we're going to do a lot of the same stuff. So I'm going to get the same dependencies, and I also need the closing data. So just to remind us, close.plot, plt.show. So we're starting with just this data. Oh. And I flipped it around for some reason. 1. All right, I guess it doesn't really matter. All right, so let's comment that out. So now what I want to do is, so before we start, what was our low pass filter window? What did that look like? Remember, that was our list that was like, if it had 2 elements, it would have been 0.5 and 0.5, right? So that they always add up to, so it's a flat, so a boxcar window, it's flat, but the sum of all of the terms has to add up to 5. So if we had 4 terms, we'd say like 0.25, 0.25, 0.25, 0.25. So that's our low pass. I'm going to comment that out so we can hang on to it. Our low pass window. So what I want to do now is create this differential window. And it's going to be a numpy.array. And it's going to be 1 and -1. Now, just like before, we need to pad it with 0. So we'll say padded is equal to dsp.0 pad diff window length of close. So it needs to be the same length as our close, our original close signal, so that way we can convolve it all the way down. So let's say this diff wave. So we need to convert into wave, dsp.wave with a capital W, wave of padded at a frame rate is going to be equal to 1, but at frame rate equals close dot frame rate. So that's our wave. Now we need to actually do the filtering. So we'll say diff underscore filter is equal to diff underscore wave dot make spectrum. And let's take a look at it. Diff underscore filter dot plot gets us a thing that looks like that. Okay, so, and what we see here is what we sort of expected, right? Because we're trying to make a high pass filter, so we're going to get this curve in the frequency domain that sort of is 0 at the low frequencies and goes up at the higher frequencies. So this filter, this window 1 and -1, just two terms, gives us this high pass filter effect. Any questions about that? All right, that's everything for that one. All right, let's move along. Okay, so let's keep talking about differentiation. So the filter from the previous, oh, that had a cool animation on it. All right, from the previous example had the same effect as calculating the first derivative of our sequel, or of our signal. Differentiation in the time domain corresponds to a filter, a simple filter, specifically a high-pass filter in the frequency domain. And we're going to demonstrate this with just a little bit of math. Suppose that we have a complex sinusoid with frequency f. So we'll say that's equal to that. Our signal f of t is equal to e to 2 pi I ft. So that's our complex sinusoid. Now the first derivative of e sub f is going to be this, right? The derivative of d with respect to d dt of e sub f of t is equal to 2 pi if times e to the 2 pi ift, right? Think back to your Cal 1 class. Now with a little bit of algebra, we can rearrange this a little bit, because this bit here, e to the 2 pi ift, is our original signal. It's still in our space, right? So now the derivative is just equal to 2 pi if times e to the t. In other words, taking the derivative of e to the f is the same as multiplying it by 2 pi if, which is a complex number with magnitude 2 pi f and an angle of pi over 2. So what does that mean? A couple of things. In linear algebra, EF is an eigenfunction of the differentiation operator. So if we go back and look at this, e to the f is that function that appears there at the end. So what does that mean? An operator is a function that takes a function as an input and returns another function as output. So if we have a function g, g is an eigenfunction of an operator a if applying a to g has the effect of multiplying the function by a scalar. So for example, if we have a times g equals lambda times g, then g is the eigenfunction. So if we go all the way back to this, right, you can see that structure there, right? d dt times e is equal to 2 pi if times e. So e is the eigenfunction in that case. Get all the way through. So yeah, so in this case, the scalar lambda is the eigenvalue that corresponds to the eigenfunction g. So in this case, our lambda is equal to that 2 pi times I times f. So a given operator might have many eigenfunctions, each with a corresponding eigenvalue. So for a complex signal, the process of differentiation is a little bit different. What we want to do first is express the signal as the sum of complex sinusoids. So as the, get its spectrum, do the decomposition. Compute the derivative of each component by multiplication. and then add up all the differentiated components to get our final signal there. And this process is identical to our algorithm for convolution, right? Where we take each of the pieces, we do the multiplication one by one, and then add them all up at the end. So that was a lot of sort of abstract stuff. Just some definitions. Let's take a look and see what we get if we do all of that in code. All right, so let's pop this up and let's call this demo3.py. All right, same thing. Let's get our dependencies. I'm gonna need numpy as MP, import pandas as PD. Well, it keeps doing that. Import think DSP as DSP, and import matplotlib.pyplot as PLT. All right, let me copy and paste our signal to get our original guy there. Now let's go ahead and get the spectrum. So I'm going to do this. I'm going to say deriv for derivative spectrum, because I'm just going to start with what we have originally. So close.make spectrum. Let's go ahead and plot it just to remind us what it looks like. Plot plt.xlim 0.05 plt.show. Right, remember this is going to be our Brownian noise, our red noise spectrum. Pandas, not pans. There we go. So just like we saw before, the spectrum of our signal is basically just red noise. So let me comment out these guys. Make a header comment here that says we're going to differentiate the spectrum. So deriv spectrum equals what we already had there. Deriv spectrum equals deriv spectrum dot differentiate. Now let's make it into a wave. Deriv equals spectrum dot make underscore wave, and let's plot that. Well, let's get a segment of it. Deriv segment is equal to deriv dot segment. Duration equals just 50. We're just going to take a look at a few pieces of it, and let's plot that. Deriv segment dot plot, and let's do this plt dot show. Actually, you know what I want to do before I take the segment is I want to look at the actual deriv signal. So deriv dot plot, and let's see what that gets us. All right, so that's basically what we saw before, right? It was sort of centered around the horizontal axis, centered around 0, and it's just those differences of each piece. If we take a look at a smaller little chunk of it there, just a segment. Segment, if I can spell segment correctly. There we go, right? So you're just going to get a little piece that's sort of centered around 0 there. So now let's go ahead and do this. I want to bring back our original diff function. Let me comment some of these guys out. So what I do now is just say, so that was differentiate that we did there on the spectrum, but if we just take diff of the original signal, the y's, convert it to a wave, and grab a segment, we should get a piece that looks approximately the same. In fact, let me just take that deriv segment, PLT, let's throw a legend on it, legend. call this dsp.differentiate, and just np.diff, or we're going to get plt.show. So we're going to plot each of these guys against us, and we should get some stuff that looks basically exactly the same if, well, it helps if you plot the thing you're trying to look at. Change segment dot plot. All right, and we get a signal that's kind of the same, but notice that it is a little bit different, right? Like our original differentiate thing has these sort of high frequency peaks. All right, the patterns are basically the same, but they're calculated a little bit differently. So you're going to see here that the result is kind of the same as it was before, but you are going to get a slight difference in your calculation. Okay, so from there, let's take a look at something else. Let me comment out that and that and that. So I want to apply some of that linear algebra to this first. So the first thing I'm going to do is say deriv underscore filter equals close dot make spectrum. So I just want that original spectrum there. And so what I'm going to do here is say deriv underscore filter dot hs, the components, is equal to dsp dot pi 2 times 1j. By the way, this is how you do, if you want to do a complex number in Python, this is the syntax for it, just 1j times deriv filter dot fs, the frequencies. And let's go ahead and plot that. Deriv filter dot plot. And plt dot show. Oh, what did we screw up? Oh, deriv filter. Okay, so see, you can see there we kind of get the same basic little thing. What is this little orange piece? It's kind of sticking on the edge there. It's kind of strange. Do I have another plot? Oh, let's comment that out. There we go. That's what we wanted to see. No, it was that piece hanging out there. So here's the take home here. So if we took the spectrum of our original signal, right? So we have closed that make spectrum. Here what we're effectively doing is taking the derivative of that spectrum and then plotting it. And you can see that we've got a high pass filter, right? 0 down at the low frequency, 1s up at the high frequency. So let's do that with a window and see what that sort of does for us. Let's keep all of that. I'm going to comment out plt.show. So here's what I'm going to do now. I'm going to say diff window is equal to np.array 1.0 minus 1.0. We're going to pad it with zeros. dsp.0pad diff window. That's the same length as close. Let's make it a wave. Diff wave is equal to dsp.wave padded frame rate matches close.frame rate. Diff filter to get the spectrum is going to be what? Diff wave dot make spectrum. And let's plot it. Diff filter dot plot. I just feel like I made some mistakes here. plt dot legend. So two pieces here. Up at the top is going to be just I'm going to call the derivative spectrum. So this was like just taking the derivative directly. And the other one here is by applying the derivative window plt.show. Nice. All right. So that's kind of what we expected. So by taking the derivative directly, mathematically, we get this like ideal high-pass filter that ramps up from 0 to 1. Right? But when we pad it with this window, we get this, still a high-pass filter, but it kind of curves off a little bit from that ideal case. And in a lot of applications, you'll find that like having this curved signal is actually preferable because it's not quite so abrupt. So you want your components to sort of fall off nice and easily instead of just being like slammed off completely. So any questions about this? So doing the derivative gives us a high pass filter. And again, the take home here basically being is integrate by a window that is 1 and minus 1 gets you a high pass filter. All right, so let's move on and talk about integration. So in the previous section, we saw that differentiation in the time domain corresponds to a simple filter, specifically a high-pass filter in the frequency domain. Since integration is the inverse of differentiation, it's also going to be a similar filter. Man, I threw a lot of code demos in here. Let's see. So let's take a look at integration, see what that gets us. So we'll create another demo file, demo4.py. And we're going to grab a lot of the same stuff. And all I really want to show here is that, well, let's see what happens if we do integration. So I'm going to start with close spectrum. So it's our same close signal as before. Close spectrum equals close dot make spectrum. Now I want to make an integration filter. So I'm going to say integrate filter equals close spectrum. Let's make a copy of this directly. Copy. And then we're going to integrate. So integ filter dot integrate. Now let's turn it into a wave. So integ wave equals integ filter dot make wave. Now let's take a look at what plotting that gets us. Integ underscore wave dot plot plt dot show. So that's kind of interesting, right? It's basically the same signal that we had before, right? So let's kind of take a look at what we did, right? So we took the spectrum, and all we did was we integrated the spectrum, and we got effectively the same signal back again. No, I started at -1. So if we flip back over again, we'll get that. So yeah, so integ wave. If all I do is just take the spectrum, so close spectrum dot plot, and run that, remember we're going to get our brown noise. And if all we do is just take the integral of our signal, of our spectrum, we basically get the exact same signal back again. So let's build on that a little bit. We're going to kind of do the same thing that we just did before. So I'm going to say integ filter equals close dot make spectrum. I think I could just use close.make spectrum, close spectrum directly. And I'm going to say this, integ filter dot h's is equal to 1 divided by dsp dot pi 2 times 1j times the frequency components integ filter dot fs, and plot that. plt.show. So we get this signal that kind of curves off, and if we go ahead and plot it on a log scale, plt dot y scale log, let's run that again. So here we get a low pass filter. So we've got the signal that, you know, our low frequency components here, we're taking a lot of them and then we're sort of falling off as the frequency components increase. And so this basically shows you that differentiation and integration are sort of both sides of the same coin, right? So if you know, differentiate your spectrum, you're going to be low pass filtering. If you integrate your, if you differentiate your spectrum, you're going to be high pass filtering. And if you integrate your spectrum, you're going to be low pass filtering. So that's the take-home punchline there. All right. So the last thing we want to do is, and I'm not even going to go back to the PowerPoint, but we're going to calculate what's called the cumulative sum, which is approximately the same thing as integrating. By adding, so remember, integration is just, you know, the area under the curve, right, from your Cal 2 class. So if we just use NumPy to just add up the signals, instead of performing an integration, we can get something that looks about the same. So I'm going to create a file called Demo5, be our last one for today. Oh, let's see. Edward asks, is there a difference between taking the forward Euler difference or the backward Euler difference or other discrete differentiation techniques? Do we get completely different filters there? So, no, you're going to get slightly different filters if you take slightly different, if you use slightly different differentiation techniques. You're still going to get a high pass filter, but the characteristics are going to be slightly different. Cool. All right. So where were we? Demo5.py. So let's do this. I need all my same dependencies here. I don't think I need pandas though. I'm going to lose pandas. I want to create a sawtooth wave. So I'm going to say signal equals dsp.sawtooth signal at a frequency of 50 hertz. Let's keep it short. 50 hertz. So I'm going to call it in wave, or like my input wave is equal to signal.make wave for just a tenth of a second, 0.1, at a frame rate of the classic 44.1 kilohertz. And let's take a look at the spectrum. So let's get in spectrum equals in underscore wave dot make spectrum. Let's plot the wave first just to see what that looks like. In wave dot plot plt dot show. We should all know what a sawtooth signal looks like. It looks like that, right? Ramps up and then drops down immediately back to its starting point. That's a sawtooth wave. Let's take a look at its spectrum. And we're going to get a signal there that is a lot of low frequency components and then these harmonics that fall off. Let's go ahead and sort of zoom in a little bit. plt.xlim, what was that, 0 to 5,000? Let's take a look at that. There we go. Oh. Blow that up. There you go. So we get our peaks at every step along the way, right? So for a signal that's just at 50 hertz, you can have a lot of harmonics as you expand out. So there we go. There's our spectrum. That's our starting point. Let's take all of these. Now we're going to create an output wave, which equals in wave dot cumulative sum. right, is basically going to do a one-shot sort of integration of our entire signal. So let's take a look and see what that looks like. Outwave.plot, plt.show. This kind of weird sort of parabolic equation. If we plot our original, let's put both of them next to each other. See what that looks like. Well, a couple of things. Notice that these valleys, these troughs, are way deeper than the sort of ramps were for our peaks. But if we add them all up, that's what we get. Let's do some manipulation here, though. Let's say I'm going to comment these guys out. Comment all these guys out. I want to do what's called unbiasing. Outwave.unbias. It's going to basically bring it down to be around 0. Let's take a look at that. Outwave.plot, plt.show. Right. In fact, let me plot both of these on top of each other. That'll make more sense to see what unbiased does. Yeah. So notice that. So the blue one was our original one that sort of just started at 0 and dropped down. By taking out the bias, we're essentially taking out the DC component and just pulling it up so that it sort of floats around where it needs to be. I wonder what happens if we plot our original wave against, I think it's still going to be sort of washed out. Yeah, but that's something. Now let's take a look at the spectrum. So out spectrum equals outwave.make spectrum out spectrum.plot. Let's go ahead and zoom in again to plt.xlim. Let's go from 0 to 5,000 again. plt.show. And where is our original spectrum? Let's take our original spectrum too. And throw a legend down. Original. Filtered. That doesn't really let us see a whole bunch. Let's go ahead and zoom in back to 1,000. So this is kind of strange. So what is going on here? This is sort of peculiar, right? Because we get, it's almost like we've amplified our lower frequency components. So I believe this is just sort of a mathematical artifact here and not a real effect that the signal is having. But the big take home here is you can see that the low frequency components are still present and they're getting driven out pretty quick. That's kind of a weird plot. All right. Last thing I want to do, that's kind of weird. Maybe we should have normalized. Is kind of see what that all looks like. Actually, do I really want to do this? Yeah, I want to do it. That'll be fun. We're going to go ahead and grab, oh, that's what I need pandas for. Pandas, import pandas. SPD. So we're going to bring in our signal again. We're going to do our differentiated filter. See what that looks like. plt.show. All right, so yeah, so our low frequency components there. Let's zoom in a little bit. Oh, stupid. Stupid. Yeah, that's really gonna look stupid. Let's see. Get rid of that. There we go. So there's our high pass filter, that differentiating high pass filter. And let's go ahead and we're gonna make a copy of that directly. So I'm gonna take you out. I'm just gonna go ahead and pull cumulative sum filter equals diff filter dot copy. So we're just going to make a copy. We're going to do some differentiation on it. So cumulative sum filter dot HS's, the amplitudes, equals 1 over filter dot HS. So we're just going to invert everything. Let's plot that. Whoa. All right, let's put that on a log scale. That's insane. There we go. Still a pretty steep low pass filter. And then let's keep that. Let's keep all of that. Let's compare it with our integration filter. So we'll start with the original spectrum. Close dot make spectrum. Integ filter dot HS equals 1 over DSP dot pi 2 times 1J times integ filter dot FS integ filter dot plot, also on the log scale. There we go. We get a signal that's basically, you know, essentially the same thing, right? It starts off at a huge number at 0, drops off pretty fast. So all of that to say, I know that was a little bit dry, but all of that to say that just simply adding up everything performs the same effect as integrating our signal, which fundamentally performs the same effect as just being a low pass filter. So if you calculate the difference between each of the steps of your signal, that's going to be the same effect as high pass filtering. If you just add up everything as you go, that's going to have the same effect as extreme low pass filtering. So any questions about any of that? All right. In that case, that is, I believe, yep, everything that I've got for y'all today. So if there are no other questions, comments, or concerns, that's it. Like I said, don't forget, we're going to take an exam 1 week from today, and we'll do a full review on Friday. On Wednesday, we'll kind of wrap up some of our Python stuff and basically just be done with all of the work that we need to do for the semester, minus your capstone project. So any other questions, comments, concerns? All right. In that case, thanks, guys. I'll see you on Wednesday.